Pleasure for me to introduce Glenn. Glenn's a colleague in control theory in the Department of Engineering at Cambridge, and he's going to speak about scalable approaches to large networks.
Right. Thank you, Richard. Thanks very much for the invitation. It's a great pleasure to be here. When Richard invited me 6 months ago, approximately, we just got a large grant from the EPSRC in the Department of Engineering, in the control group of the Department of Engineering, looking at these power networks and all various energy questions. So I think it was reasonable to assume on both of our parts that I'd actually have something to say about power systems today. As it's turned out, I think these power networks, I never thought it would be easy, but they're a lot harder than I did ever imagined. There's a lot of tricky issues. So the talk will be, I'll start off just talking about general approach to the control of large systems, and then we'll talk a bit about some of the issues with power networks at the end. To put it into context, I'm talking, even though the sorts of techniques I should be talking about potentially have application to some of the economic questions that Sean was talking about this morning, particularly the price oscillations due to the ramp constraints and things like that. That's not the area. That's not the main focus of this talk. I'm really thinking about the much shorter time scale of oscillations. So the actual physical network, where the oscillations are of the order of a few seconds, is the slowest. So, large systems. So I'm a control engineer. My sort of bread and butter was looking at this sort of control problem. So I sort of worked for a few years on designing the control systems on this aircraft when I first graduated. But typical control problems where you've got a fixed architecture, so an aircraft to be controlled, a small fixed number of inputs, the control surfaces on the wings, the thrust of the engines, and a small and, importantly, fixed number of measurements, the accelerations, angular velocities and things like that. I think these sorts of control problems are now sort of well understood. But so the new challenge for me and a lot of people working in the control area is these large networks where the dots there, the nodes on this graph are all dynamical systems. Have we got a pointer? Is there a? Oh, okay. Oh, a physical pointer, right? Okay. That's fine. So the nodes are here dynamical systems. So I call this a sort of feedback network rather than a. That's the danger of that, yes. Rather than a graph, because the nodes here are representing dynamical systems. So there's differential equations associated with each node, and those nodes are getting information from neighbors and transferring information back to neighbors. So there are many sorts of problems you can put in this type of picture. By colouring the dots different colours, I'm trying to emphasise there's a heterogeneity here. I'm not talking about graphs where or networks where the nodes are the same systems copied many times over, or indeed where they're sort of low order, first order integrators or something. Typically, I'm thinking of complex dynamical systems here, and they're different. So examples of this: economic networks, power distribution networks, as in today, communication networks, for example, flow control on the internet, which is where I started working on these sorts of issues, and formations of vehicles. So looking at the way that things might form in, or satellites, etc., forming formations. Looking at platooning of cars, all sort of fit into this sorts of picture. So we've looked quite a lot at the last one as well. But the picture, or the questions I'm interested in are: is there a way of predicting the global properties of such a network from the properties of the individual systems and the local interactions, the interactions with their neighbour? So there's a sort of history of this in sort of statistical mechanics, where you're using sort of rather toy, simple models for the nodes. But when we've got complex dynamical systems at these nodes, can we predict global properties from the local information, from the local interactions? And I think more importantly, can we find design rules? Can we find ways of designing dynamics for the agents and designing the local interactions, which ensure that the global behaviour is desirable in some sense? And that's a bit strong to say yes, but in some, it's certainly in some examples you can do this, and the language I'll be talking about is in terms of sort of modules and protocols. So think of sort of Lego bricks, where you've got green, yellow, red bricks, all of the different dynamics. What we're trying to come up with is rules by which you're allowed to assemble these together, where the assembly means you're setting up some sort of feedback interaction. And the protocols tell you how you can connect them together. I'll give examples. So the precise statement, the precise statement just looking at a little bit of that graph, is that each vertex is a stable linear dynamical system with an output y and an input u. So and the u's are the average of the so the input to system G2 is the average of the output of system G4, which is the y4, plus the output of system G3, which is y3. Yeah. So just sums those divided by the by the integree. Yeah. So so these are linear dynamical systems. Each of them is say taking the average of the inputs and copying its output to its neighbours. So at this point, okay. So and then we have a theorem which I'll state in a minute, which is that as long as each system satisfies a sort of a Nyquist-like stability condition with its neighbours, then the network is guaranteed to be stable. Now, you're not all control engineers here, so let's talk a bit, just to remind you what a lot of you, apologies to those of you who this is totally familiar to, but I think even people who've done the Nyquist stability theorem as an undergraduate and have not used it since, it's worth going through it again, because it's incredibly powerful theorem. It's a incredibly powerful viewpoint, a way of looking at dynamical systems with feedback. So if you take the standard feedback loop, so I've got a system here, G, where G of j omega is the harmonic response, or the transfer function of the system. If I stuck a sinusoid in U, then the output Y in steady state will be a sinusoid of magnitude being the magnitude of G, and phase shift relative to the input being the argument of G at the particular frequency. If I close feedback around that with a feedback gain of K, the Nyquist stability theorem tells us that, well, in the case where this is stable, then the interconnection is going to be stable if and only if the locus of this object, of G of j omega, doesn't go around -1. So if you plot K times G, and you get this curve, if it doesn't go around -1, then the feedback system is stable. And if it does, then the feedback system is unstable. Okay. So why am I talking about this? All sort of, we had a bit of economics 101 in the previous talk, So why am I doing control 101? Well, to try and justify, a lot of this talk is going to be about linear systems. So why are linear systems interesting? Clearly, power systems are nonlinear. So shouldn't we just ignore linear systems theory? Well, I don't think so, because I think you can still get a lot from linear systems. So let me sort of continue that justification. It's one of my favorite toys. And my kids as well. And the engineers and the Cambridge undergraduates. So I use this in the sort of, in Control 101. It's called Paper 6 in England, to demonstrate feedback. So it's a simple, it's a Lego version of the Segway. And if I turn the controller on, got a little, if it talks, yeah, I've got a little PlayStation controller here, so I can make it do things. Bit of a small stage for it to be operating on, but hopefully it means you can see it. So it's just a, yeah, so it balances, and it's made out of Lego. So how does it do it? And this is actually how I start the second year sort of introductory control course, get the students thinking about how that's achieved. I think to most people here it'd be, it's pretty obvious, but I give the students options of is there some sort of complex logic going on inside that it detects if it's being pushed and leans against it, and things like that. So if it hits a disturbance, does it fight back? Is there loads of code with ifs and then if then statements inside? Well, no. The actual code is pretty much one line. It's just that the power into the motor, so there's a couple of motors here. The motor power there is a linear combination of the angle that the wheels have gone round, the angular velocity of the wheels, and then there's a gyroscope here. So on the end there's a rate gyro, so that's measuring the angular velocity, and that's integrated up to give an angle. So very simple, linear feedback. Linear feedback does work, even though the system itself is clearly nonlinear. It's Lego, for goodness sake. It wobbles, and it's not particularly rigid, for example. And the motors are highly nonlinear. However, the numbers do matter. If I change, I don't know how I stop that thing coming up, but. Does anyone know? I don't normally present with this. Does anyone know if I can get rid of that? No, that'd be too. I saw you use that. Yeah, never mind. If I change that 0.35 to a 0.55, then it doesn't work. Yeah. So. Very small change, yeah? 50% or something. Yeah? And it took, and when I was designing this, I initially thought it'd be easy, because we've got inverted pendulums in the department, and I thought I'd just be able to sort of throw the thing together and just pluck out some numbers and get the thing to balance. I'm a control engineer, I've been doing this for years, sort of thing. I couldn't. I spent a whole day on it with my son and just couldn't get it to work. So I ended up having to had to get the ruler out, had to measure it and put it on the kitchen scales, and estimate moments of inertia, and then produce a differential equation and do it properly. Yeah, but it works. Yeah, so it's a simple linear feedback, and this is often the case with these sort of with linear feedback like this. When you've got it right, it's incredibly robust. I mean, I picked this up. This was in bits last night because my son had various bits of it in different models. So I picked it. Well, actually, I couldn't find most of them, and he'd gone to bed by the time I got home last night. So I had to get the bits out this morning, threw it together, put the software on, and it works. So it's robust, but the numbers are important. How does the Nyquist stability criterion relate to this? So if it's a block diagram like I had before, so I've got the motor power, got the actual physical Lego Segway, the brick on it here is sensing all the information, and that's actually got the computer inside, little ARM chip, and that's determining the motor power. These are the measurements of the wheel position and the angular velocity. So I did some tests where I just injected the sinusoid. So we get a sinusoidal variation with going into the motor power, sinusoid coming out, and then if you look at just the ratio of amplitudes and phases between the input and the output, you can actually draw one of these Nyquist diagrams experimentally. So that's what it comes out as. It's a bit, the system is unstable to start with, so it's a little bit more complex than the simple statement I gave before. But basically, the curve leaves the -1 point to the left, so it should be stable, just as it actually is. Sorry? I have no idea. No, I don't think so. But it's certainly unstable if it's got two unstable poles. If you do the mirror image and the bits at infinity and stuff, there's actually two counterclockwise encirclements. But if I change the overall gain, if I were to multiply that by 1.7, then that curve gets bigger. Yeah. So before the because this, and the reason why sorry, this is sort of undergraduate stuff again, but the reason why this Nyquist stability way of looking at things is so good is that it's linear in the thing you're controlling and the controller. Yeah. If I multiply the controller by 1.7, make all these numbers 70% bigger, then I've just made this picture 70% bigger. Yeah. And if I do that, then this crucial -1 point ends up on the curve, and I get this prediction that the thing should go unstable at a frequency of 30 radians per second. And if I do that, so literally just put that code inside, which I think is that one. So that's about 30 radians per second, or 5 hertz. Yeah. And if I turn it up the gain any higher, the oscillations would build up, and it would go unstable. If I decrease that number so the gains are all 60% of what they were before, then this curve gets smaller, and -1 pops out the other side of it. And I've chosen the gain so that -1 is slightly outside there. And it predicts an instability of around 4.5, 5 radians per second. And that's this one, I think. So it's only just on the edge of instability. It may or may not go, depending on what the temperature is and things like that. The model does change, and how long the motors have been running for. The characteristics do change as they've been running a bit. So it's not very good. Right. So the final point about linear systems, even though power systems clearly are nonlinear, and a lot of the interesting characteristics in power systems, like cascading failures, are very nonlinear things. Well, so is this thing falling over. But the prediction about it was linear. If you've got, imagine you had 100 of these. There is a sort of analogy, because it's linear, if you push that over too far,
it will be in the nonlinear range, and it's likely to fall over.
That's right. But whether it gets that nonlinear regime is depends upon the underlying small signal linear stability. Yeah. No, I was just going to say. So imagine you had 100 of these in a room, all trying to keep a certain distance from the one next door, which is pretty much like, a bit like a sort of power systems network. And then you're interested, if I knocked one over, are they all going to fall over? So that would be the sort of cascading failure. Well, clearly they're much less. That's much less likely to happen if the underlying stability is better. Yeah. Anyway, so now let me just state the network version of that. That's the sort of the interesting bit, I think. As I had the top bit before, and the theorem is that if each system, I said the theorem before, so the precise statement is, rather than plotting the Nyquist diagram for one of these loops, so let's go back remember that the picture is this. So the feedback loops are products of two G's. So to go around one of these loops, so the input to G2 is, part of the input to G2 is the output of G3, and part of the input to G3 is the output from G2. So to go around a loop, I've got a product of G's there, and so yeah, the theorem is that I take those products and I find something which is a bit bigger than the convex hull of the products here, where I keep the I fixed and I vary the K over the systems it's connected to. So this is all the sort of pairwise interconnections around, say, for I fixed. Take this thing, which I call the S hull. It's you take the square root of the set of complex numbers, you take their convex hull and you square it back up. So you end up with something which is a bit. So this S hull of these 4 points is the interior of the red curve there, which is a bit bigger than the convex hull. It actually can be quite a lot bigger than the convex hull, because if I took away the point at the origin, the red curve wouldn't change, but the convex hull would get rather smaller. I don't know if this is actually called anything. I mean, I keep giving talks where I call this an S hull to different audiences, hoping that someone's seen something like it before, and maybe it's got a name. Hasn't happened, so maybe probably not. But notice this is an entirely decentralized condition, yeah? In that you take this, forming these hulls here, you do it frequency by frequency, yeah? So it's not necessarily too conservative, you just take one frequency. You index over the system, so you go through, so system I, he just needs to know the frequency response of the guy he's next to, and so he can work out this set frequency by frequency. He can check whether one doesn't intersect with that. This convex hull has to be done over the whole network. Well, basically, so the whole everyone could agree some half plane, so some line that goes through the point sort of -1 back here, and we'll keep our S hulls on the same side of that line. It doesn't have to be a vertical line; it can be a slanting line. So apart from that, it's an entirely decentralized condition. Just as an aside to control people here, there are many sort of results which sound superficially similar to this, based on, for example, on passivity type results, but they all depend on the properties of individual systems. Yeah? So if I take lots of systems which are passive with respect to some sort of dissipation function, I can connect them up, then the interconnection is going to be passive. But that's a property of the individual systems, where the result here depends upon the properties of the loops. So it's what you're connected to. So it's rather different. To give an example of this modules and protocols, just going back a bit, Frank will recognise this from the internet. It's basically a toy example of the internet congestion thing we were looking at a few years ago. But if I say I've got green systems and red systems, the green systems represent so the rate of change of the output is the delayed input. So it's an integrator with delay and some scaling based on the n and the t. And I've got red systems which are just first order differential equations with a time constant tau, and again some gains. And imagine these are Lego bricks. Each one has got its parameters, its time constant t, and its gain kg written on the side, and maybe the red ones have got the tau written on the side, and their k. But they're all different. I mean, pick up a red brick, and it might have all my red bricks have got different tau's on them. All my green bricks have got different t's, and I want to know if I connect all these together, is the interconnection going to be stable? And I'll say, well, let's come up with a protocol. I'll allow myself to connect these two together if the product of the gains is less or equal to 1 and the time constant of the red one, the time constant of the differential equation, is no greater than twice the delay on the green one. And then the picture in my when I pictured the network corresponding to that was just that. So it corresponds to the block diagram I just had. And just want to point out that, just to emphasize that each green system has potentially got a different capital T, each red a different tau, and each red module can be connected to many green modules, each green to many reds. So the picture is I start off with a green, I pick a red, satisfying the interconnection rules, put the two together in this feedback interconnection. I then carry on adding reds and carry on adding greens, so building up a big network of these red and green systems, arbitrarily sized. And the only condition is when I add a new thing on, it will be bound onto one existing brick. When I add a new thing on, it's got to satisfy those rules. And it turns out that you can prove that that any system you get following that by going through that process is stable. Yeah? And there's a graph. This is just looking at these S-hull things, frequency by frequency, and taking the convex hull, which is that red curve there, and that doesn't go around -1. So anything you get by doing this, any interconnection you get, any network you get by following these rules is guaranteed to be stable. Now, it's a toy example, but I think it's still fairly powerful, because I know no other way, even for that simple system. You know, so it was just first order dynamics at each node. I know no other way of proving stability. I don't think. I mean, we spent some time looking for Lyapunov functions and things like that, other ways of approaching this problem. But I know no other way of proving that putting these things together, you always end up with a stable system. The details ought to give a hint at for this audience. So when we take the Laplace transform, so I had Jeremy with us before for the sort of harmonic response operator. Got S there instead, but it's the same object. So these are the equations I gave. I've got two systems, F and G, so I've used now Y for the outputs of the F's and U's for the outputs of the G's. The input's been added up. This was the, so that was the condition of stability. It turns out that for bipartite systems like this, you only actually have to take the S hulls over either the red or the greens. But that's a little detail that doesn't really matter here. And the reason is it's just a statement about numerical ranges. So if I put this into a matrix form, I'd have Y is equal to a diagonal matrix of F's times this interconnection, which I'm calling the R here, R hat, times the U's. U is equal to the G's times the same thing transposed times Y. So there is a symmetry here I should have mentioned. There's a symmetry underlying all of this, which I probably should have mentioned earlier. And then there's this restriction on size, which is just general. It's just a bit slightly more general than the take and the average. Essentially, you can take weighted averages instead there. And if you look at the union of the numerical range of this operator, which is precisely the thing that you draw the Nyquist diagram of, or in this multivariable case, you draw the loci of the eigenvalues of this thing, when you've got a system like this with many inputs and outputs. So using numerical range to bound that spectrum, if you take the union over all possible interconnection, or all possible weights, these R's, which are composed of the which are the non-zero elements there are related to the D's, where the connections are. If you look at all possible all possible R's, so all possible weights, take the numerical range, it's essentially saying all possible interconnections, then this, what was I saying, sorry, the union of all those numerical ranges is precisely this convex hull of S hulls that I introduced. So it's not a it looks like this is a highly conservative condition for stability, but it's not in the sense of if you want to guarantee stability for all possible ways of connecting these things together, it's actually necessarily sufficient. Sorry, apart from, that's going too far, apart from the numerical range is obviously just a bound on the eigenvalues. Yeah. So the only conservativeness, if you look over all networks, the only conservativeness is in using the numerical range to bound the spectrum. So this started with looking at internet, where it was quite successful. But let me go on to power systems. And the question is, does this apply? And I said there's no, don't get your hopes up. There's no basically, the internet was a lot easier than power systems. So let's just talk a little bit about power systems. So power networks are the standard picture, as Sean mentioned this morning. You've got if you just got generators and passive loads connected together, you've just got a bunch of springs, springs and masses with a bit of damping. So inherently, they're only marginally stable or close to marginally stable. If you start, as soon as you put voltage regulators on at the generators, then they're very easily destabilized. And stability is then introduced, the standard picture, by putting on power system stabilizers and flexible AC devices like static VAR compensators. So an example, sort of just to talk about these terms, an example that's been sort of well looked at is this simple 4-generator model, sort of benchmark that Kundar has in his book, and there's a previous paper, where so there's 4 generators, 2 closely coupled here, 2 closely coupled in another area over there, with a connection, sort of long distance weak connection between them, and there's potential for all sorts of oscillations here. The local area nodes where the local machines are oscillating against each other, so there's a power flow from one machine into another. And the inter-area modes where there's power fluctuations from one side to the other. So these voltage regulators, we should put on to control the terminal voltage here, Vt, by controlling the excitation, so often called exciters. So the action of stabilising the terminal voltage on the generator is can often be destabilising. So power system stabilisers, for example, might be put on looking at the angular velocity of the generator and putting another feedback loop onto the onto the field, onto the field windings on the generator. So this is just the example out of out of MATLAB for that model. This is put a fault onto one of those lines, and then clear it. Look at the change in the angles of 3 of the machines relative to the 4th, the angular velocity, and the acceleration power. So the difference between the power coming in from the prime mover and the electrical power going out. Yes, and this is with the voltage regulator put on for one particular configuration, one particular scenario where the thing goes unstable. And then if you put, this is a standard little example, you put the power system stabilizer on, and for the same faults you get stable behavior. So the question is, well, let's just go on a bit first. How are these things tuned? I'm aware there are people in the audience who probably know a lot more about this than or about practice than I do. But as far as I can ascertain, these stabilizing devices, whether they be the power system stabilizers as here, or SVCs or other other electronic sort of means. These things are tuned as part of the commissioning process when you put a generator in, or a line in, and may be tweaked with time. But basically, they're very much like the controllers that I was sort of designing here. Controllers have been designed on the local machines to get the thing working at the time that it's connected to the grid. But there's an obvious issue there. I mean, the network changes. So when you start adding new bits to the network, you might have to go back and change the parameters of the model. And things get much worse when you start adding renewable energy, for example. Any other when you diversify the supply, so rather than having a few large generators where you have to put these stabilizers on, if you've got hundreds and thousands of small generators dotted over the country, well, how do you stabilize those? The situation at the moment is that basically a lot of the smaller scale generation, or all of the smaller scale generation, will just relying on the fact that there's a 50 hertz signal going up and down, and just inject power without doing anything to help the stability of that signal. Yeah. So and basically, clearly, there's a limit to how much asynchronous power you can put in that way. Yeah. As you reduce the amount of power coming in from these large the large generators, you're going to have to do much more. But basically, the high power electronics, where you're injecting the power into the network, is going to have to be doing more.
What would you classify asynchronous electrical machines as in the early wind turbines?
They do.
Sort of squirrel cage type. Yeah. They're not synchronous like this, are they? They don't.
Right.
Yeah.
Just, David, I think I know what you're trying to ask. Point of clarification about the last point. It's a very broad statement.
Oh, absolutely. Yeah. I do not stand up here as an expert on this.
And in fact, on a stability basis, for low penetration, some of these devices can have a stabilizing effect with respect to some issues.
Oh, potentially.
The statement is far too broad. I mean, doubly fed induction generators at low penetration levels have a very beneficial. They're very beneficial for voltage stability, for example, sometimes, depending on how you operate them.
That would come into reversal, though, yeah.
Sometimes they're good, sometimes they're bad. So the statement is far too broad. Renewable
Even
energy, so
asynchronous-
they're off-
Okay, they're not actively stabilizing. Is that,
The power electronics inside a WFET induction generator is incredibly active and incredibly important.
but they're not. But surely it's just synchronized into the local grid frequency. It's not changing the power it's delivering in response to the frequency that it sees. Is
Yeah,
it?
on an active power base.
Yeah.
I'm talking about a reactive power
Reactive,
base.
I suppose.
Okay, yeah, sure.
And a lot of the stability issues in
Yeah.
networks are reactive rather than
Sure, absolutely. Yes, yes,
So
yes.
on an active power basis, the statement is somewhat correct. On a reactive power basis, it's not.
Because it's just the action of adding the inverter associated with
Yeah,
one of
because
these things
the inverter-
is providing
the
is
inverter is a
stabilizing
power
the active.
electronics device
Yeah.
and has a lot of functionality that can be very beneficial.
Right.
So,
So
said a junction generator does not have inertial response in terms of real power injection.
yeah.
That can be a bad, but it's a sort of a, it's not a very clear picture. There's many different facets.
Oh, sure. Okay, I'll accept that certainly. Yeah. So I just want to on this. So this particular example. Yeah, I think actually I'll go back to. So on that. I mean, there are, I mean, there's an old sort of early '90s paper which was looking at this network, and they were making statements like, what's the effect of having different loads here? So if you used a sort of nonlinear load model rather than a passive node model here, then it was stabilizing if if there was power flow across this interconnect, then having a nonlinear load was stabilizing on one side of the interconnect and destabilizing on the other, and sort of many sort of statements like that, where yeah, so the action of changing something has a different effect depending on where you put it on, and as far as I can work out, that's pretty much still state of the art. Is that too strong a statement? I mean, all you can do is model it and see what happens. Yeah. Whether a particular thing is going to be enhance the stability or not. Yeah.
That's very true. The parameters of the load have a big effect on the voltage stability.
Yeah.
And the problem is we often don't know what those parameters are.
Sure. Yeah. Yes. Yeah. And this is just looking at that. This particular example. This is looking at these. This is looking at the eigenvalues of this. The thing you'd look at for the Nyquist stability criterion for that two-area network. So there's multivariable. It's looking at eigenvalues. The sort of thing that if I was trying to improve stability using the techniques I was talking about, I'd be looking at going through. This is all frequencies at once. But I'd be looking through this frequency by frequency, trying to looking at some convex hulls and things. If you look at the difference, this is without the power system stabilizer, and if you add the power system stabilizer, this all that changes is the bit that's important is this curve here, which here goes one side of -1, and then just to a control engineer, that's scary. How much that corresponds to what's out there, I don't know. Obviously, I mean, this is an example done by sort of top guys in the field.
Using
So,
the method, could you see the impact of decompensation?
oh, sure. The whole idea of using those holes is that you can pick up phase. Yeah.
And you can see that.
Yeah.
Kind of the square root.
Yeah. You capture enough. You just capture enough phase information. That was the whole. That was the whole idea. That condition between the towers and the T's was precisely about how much lag's tolerated and things like that. But this is too delicate. You couldn't pick this up. So.
But my question was,
yeah.
how do you see how to fix it? I mean, you see now it's an intuition about the value of the recombination. You get a crude idea of control design.
That's the idea. I don't know. I mean, this is as far as we've got with this, basically. The situation is much more complex than you could with the internet. You precisely could make those statements in the internet. It's all put in the right thing in the right, and it's the interaction between time constants at different places. Yes, here there's so much else going on. I hope so. That's the intention.
Can I ask the other question related to
Yeah.
the approach, and that is that the assumption is that the interaction is limited to the nearest neighbour. Now, that's likely to be transgressed in a lot of realistic power systems.
Well, or your nearest neighbour is defined as as where the interaction is.
Yeah. Because that's how you guaranteed the overall system stability, isn't it?
Yeah, yeah.
I think it's a very laudable aim, because I think we are moving towards power systems where we're not going to be able to use conventional models to guarantee that they're stable. We just keep our fingers crossed.
Right. Yeah.
No, but, sure. I mean, you're not assuming that they're independent.
No.
I mean, the neighbors are still connected to the intermediary.
That's right. Yes.
If you assume this global stability, there's something.
Yeah. So we're talking about how far do I have to go back? Yeah, a long way back.
Yeah.
No, these sorts of things, where there's still an interaction between that guy and that guy, of course.
Yeah.
It's just it's coming via that. It's just all I'm saying is that mathematically, I want to be able to write it in the way that those interactions.
Well, the thing about power system is that everything is connected to everything else. It means if you constrain your connections only to the neighbor, I think it is too strong assumption. The electromagnetic forces which link all the generators through the whole system, and the interaction is not only through the neighbors, it's through everything else which is around it, and the way those controllers are tuned. You are right, they are tuned on the decentralized basis, but they are tuned in such a assuming certain security margin that the whole system is stable. So basically, those kind of things have been looked very well in the kind of 80s when the first instability phenomena was discovered. And by the 90s, I think the theory has been well developed on the whole thing.
I disagree. I don't think there is any theory. Apart from, we'll have a big model of the whole system.
Well, also you mentioned you've looked at Lyapunov function. I mean, there was the whole theory of energy-based Lyapunov functions developed based on so-called equal area criterion.
Sure.
For the whole system. So there is whole theory on the simplified assumptions, but you can use the stability of the whole system using Lyapunov theory. There were books by Pai and Pavela in Belgium, and they did look at those kind of problems.
How do you apply that to truly complex power systems, Yanis, where there will be thousands of controllers active in real time, or hundreds of thousands, or millions even?
Well, we can talk here of this, but
you can apply that then?
The picture here is that the picture here is that the network's so complex that no one's got a model of it. Yeah?
I would disagree. There are models.
Well, if
there are models, but they are big and complicated, and there's no easy answer.
yeah, and as they get bigger, but then as you get more, CHPs, sort of local things plugged into the network, then will you not reach a stage eventually where there isn't no one knows exactly what's there at any particular time? Yeah.
Isn't it true that if this thing is governed by Kirchhoff's laws, then your model is substantially correct, because you can draw it as nodes, and so even though there are one node will affect another, it can only do it via the local connection.
Sure, yes.
Magnetic
Yes.
wave. Am I misunderstanding it?
Yeah, no, that was precisely, yes.
interactions in an electrical circuit in that way must be local if they obey Kirchhoff's laws. Is that correct?
Yeah. So I mean that was I missed out the final slide, which was that it fits into this picture because you sum up well either power and reactive power or currents, some at the nodes, and the voltages, the real and reactive voltages are the shared variables. Yeah.
I think what may happen, what may be the kind of thing we're talking about, is that out of that may emerge bigger coordinations by groups of nodes working together, being synchronized. That's quite possible. But it'd still do it by the local interactions.
Yes. Yes. Yeah.
But that,
Yeah.
I mean, definitely, you can imagine you might be able to get better robustness by having more, larger communication, say making the network more dense, and then the analysis, application of the method might be more difficult.
If you put in more links.
Yeah,
Yes.
and more the information, because we know that from consensus theory and all that having more
More information is good. Yeah. Yes. So if you start sharing sort of centralized information in some way, yes. Yeah. Yeah.
At least it's still good for a approach. I mean, it's still a homogeneous controlled architecture.
That's right. So the idea, yeah, that would be the hope. I mean, it's not going to solve. It's not like the internet where you've got so much control of what's actually happening to each node, because there isn't that much heterogeneity. It's not going to answer anything, but it may give hints.
Incredible tool.
Yeah.
In your variables, do you also have rates of change, or are you simply saying this is the state, this is the voltage? Or are you actually, can you use as inputs rate of change?
Oh, well, they're fully dynamic. I mean, it's just a full time history. Everything's a function. It's a fully dynamic thing. Yes. So yes, all derivatives. Yeah.
I mean, I still don't understand what's really the point which you are trying to make. Because as I said, there is network stability, power network stability theory, and there are well-established tools when people calculate eigenvalues.
Sure.
Network sensitivity of eigenvalues. If you change one of the parameters, how the eigenvalues move to the left or the right, and etc.
Yeah.
And this is how all the tuning of, which you have mentioned, tuning of power system stabilizers is devised.
Yes. So this is all centralized control. That's all centralized control.
It is centralized control, but done in decentralized manner through individual PSSs. So what's really the point you are trying to make over here?
Oh, it is precisely that. If you got you run on something. Yes.
Say what you said
Okay, well, Frank. Yeah.
So if you think of trying to stabilize, say, the internet, and the flow control when you're downloading the document, it's a flow, and it speeds up and slows down according to the congestion in the network. And so there is a control aspect to that, there's a stabilization aspect. But you certainly do not want, every time a new document is downloaded, every time another user comes on, to have to remodel the system. You want to have the protocol designed so that whatever documents are being downloaded, the system is certifiably stable. So that's what Brendan described earlier. And presumably the point here is that you're moving to a network where it's going to be very hard to say what the network will look like in a week's time. There'll be microgeneration here or there, there'll be wind here or there, there'll be, so one doesn't want one-off proofs of stability for a given network, given that the topology and nodes of the network can change hourly or daily or whatever. But Glenn, I have a question of the very naive outsider who doesn't really understand what's going on here. But how should I imagine the current network? Is the following a mental model that's completely off? So you have these big generators, they're turning around and they're producing, say, three-phase sinusoids at 50 cycles a second.
Yeah.
And is it the case that within an area, we heard yesterday about 3 areas in the US, that within an area, the generators are all linked together? That is, that if you told me the phase of one of them, the angle the turbine of the circulating thing was at, I could deduce what the angles the others were at.
Well, they're synchronized, but they can oscillate. The local ones can oscillate against each other just as well as the.
I understood the
They're all the
point.
same speed.
So,
They go at the same speed.
They go at the same speed of meters second.
it's to do with complexity, because you've outlined the standard power system analysis stability,
Sure. Yeah.
where there's a reasonably fixed number of
of controllers and a reasonably fixed number size to the matrix. And I think what's being suggested is, could you believe that you would extend that to have, you know, potentially millions of actively controlled micro CHP units or PV systems or windmills? Or would you have to look for a different sort of methodology to guarantee stability? Or that's the message I'm.
Yes, yes. So the picture, the picture I have in my head is, so you're connecting your microgeneration on via some inverter. What can you do? That inverter can have parameters in. It could just synchronize to the local frequency, put in the power at that frequency, or it could react to the local frequency, both real and reactive power. Both in the real and reactive bits. So there's parameters. Is there a way of designing the dynamics of that box such that when you connect it up to the grid, you look at the parameters of what you're connected in. What's the length of the local line? What's the distance between there and the next the next node? Some characteristics of that line, and then here's some rules. There's the grid code that tells you, right, if you've connected it to this, then this is how you set parameters. Is there a way of doing that such that these things actually help the stability? They're not going to guarantee the stability, but could they help it?
I think we're talking about stability. There's a little bit of confusion because different types of stability in a power system. What your presentation was about electromechanical stability of rotating masses in the system.
Well, the small signal,
small signal stability.
Small signal stability, which may not have rotating masses.
But that's electromechanical stability of rotating masses, and that's to do with the regulation.
At the moment.
Now the last question was about micro CHP, all kind of controllers. I don't think they will affect electromechanical stability, because we are talking about the time scale of a second or a couple of seconds, but they might affect frequencies, so-called frequency stability. And Mark O'Malley over there in the back is the expert in those kind of things, because there are problems in Irish system, and that's a frequency stability is to do with how the power output, the real power output of generators change with changing frequency of the system.
Yeah.
So, and then the framework for frequency stability, mathematical framework for frequency stability, is different than with the electromechanical stability, because now we are talking about time scale of about 1 minute. So basically it's much longer, and then all the actions of all the other controllers, like
So what do you mean by the electromechanical? You mean the actual the regulators, the governors?
Well, I'm saying for electromechanical stability, small signal stability, you are talking about the time scale is about 1 second. Because it's very fast. Now, for frequency stability, the time of response of those devices, which is required, is in the range of is about 1 minute. So basically, it's much longer.
Sure.
And
that's the governors on the prime movers.
That's the governors on the prime movers.
Yes,
so it's completely different time scale, and quite often people completely use it different mathematical framework. So mixing the two in one framework can be confusing. So what I'm saying is that basically we should think about those two separately.
And then there's voltage stability.
There's voltage stability, which is a bit more complicated. And then we are talking about microseconds. Time scale below 1 second.
Sure, yeah.
Microseconds.
I'm glad Yanis made his contribution at last. Thanks, Yanis. But just a general point. I mean, one of the things is that, Yanis is right. Okay, that's Yanis has stated very clearly. But one of the things is that an electrical power system is fundamentally a passive circuit. Right, Yanis? It's fundamentally a passive circuit, isn't it?
The circuit itself.
Huh?
The circuit is mainly, but not the generator.
Yeah, and I'd be feared about people, no disrespect to control engineers, going in there and trying to, I'll give a bit more control, and now you're introducing more things that are dynamic. You might actually cause more trouble than you solve.
Oh, sure.
Yeah. I mean, a good old-fashioned passive circuit obeys Kirchhoff's laws. Which, we understand them. It's it's very robust. Except the PSSEs are there when something else happens, so they're active. But you just want to be a bit careful about putting in technology. Maybe we should keep it simple. The power system has worked very effectively for a long time. You've heard of KISS, keep it simple, stupid.
Oh, sure, yeah.
So there might be an element of introducing control where it's not actually of an antiquated. I'm not saying that's true. I'm simply putting it out there as a statement.
But the control, but you've got to do if you're putting this microgeneration on, you've got to do something.
Why?
Well, unless you put in lots of rotating masses at each point and use your microgeneration to heat water and drive turbines.
Okay, so why? Why if I put lots of microgeneration, what happens?
Rather than using a just. So the alternative would have some DC inverter.
Do we in this room here? I mean, every person in the audience here lives in a house or whatever and consumes electricity.
Yeah.
And then they start generating it. What's the difference? We don't control them, do we? Does the national grid control your house at the moment? No, they don't. So if you decide to generate inside your house, does it make any difference?
Or it depends on what the penetration is, doesn't it?
It might be that you
Yeah.
get
Well,
one difference is that you, depending on what technologies you're using to generate, you get more disturbances. That's the classic value of wind.
Well, just one big difference. So I don't know about the power grids, but I know about the internet. I've been working on it for 30 years. One difference is if you have tens of millions of generators, then you have potential flash valve, what we call slash dot effects. And so essentially, if you get synchronized generation at an unexpected point in time from many places, then you have a sync tree, which is completely different from a system where you have a small number of generators and a large number of consumers. And that is a problem that we face today in the internet when a large number of synchronized sources start up. It's called a botnet or a denial of service attack. And those systems are synchronized by external events and nothing to do with the network. If I broadcast on TV saying, if you go to this website, you'll get a free iPad, then 1 billion people go to this website. And that's, that is, I mean, maybe you have a solution to that, but it sounds to me like you don't. And it sounds like it's completely different from a large number of sinks with a small number of sources.
Okay, hold on. The UK has 60 million people living in it, yeah? Approximately. They all consume electricity at an arbitrary, I don't see what, I can't see the difference if some of them start to generate themselves a little bit. What's the difference?
But it's a different kind of generation. When you've got large generators with big rotating turbines, you've got more inertia there, so you've got kind of like more rotating mass. So the guys, there's a group of guys in the Netherlands, a company Power Matcher, that are actually doing micro CHP and actually trying to coordinate things, and they have problems with maintaining maintaining frequency stability because micro CHP doesn't behave the same way that a generator does. So it's a different kind of circuit. So
and the same is going on in wind. There's a worry that wind displaces conventional plant and the total inertia on the system goes down, and then your dynamics change, which is true.
This conversation's all over the place. I mean, some persons mentioned inertia, which is fine. I mean, not we all know, but some of us know about inertia. I mean, there's a little bit of confusion going on here. Are you talking about the fact that the system becomes unstable because everyone decides to turn on the microgeneration at once? Or are you talking about the fact that when there's a large strip of the generator, there's not enough inertial response and the system stabilizes it? Which problem are we discussing here? We're jumping around here a bit.
About, yeah. My personal belief is that the small microgenerators, the ones on domestic premises, are going to be probably less than loads that you can put in. And therefore that there probably isn't an issue unless maybe people want to get a bit clever and they start using them for frequency support and maybe voltage support. Then you have the potential to make things better, but perhaps you have the potential to make things worse.
One place I see a potential issue that synchronization might happen is that everybody responds to a price at once. So then there's an interesting issue. At the moment, we're all passive users of electricity. Turn it off. And even if we're microgeneration, we're essentially passive. But if we're all become clever and start responding to a price, then all of a sudden everyone might act together, and then you might have a big problem. And that's definitely an issue, for sure. But look, to be honest with you, this conversation has gone across the entire spectrum of dynamics, up and down, left and right. It is somewhat confusing.
And that's probably my fault for
Yanis will give a tutorial tomorrow at 7:30 in advance.
Trying to bring things back to Glenn, what I think Glenn was talking about, which I think is a really interesting point, is these days people who study the stability of the system are the system planners and system operators, and it's a very big job. And the more generators come in the system at the same time, the more difficult their job is because they have to look at a wide variety of conditions. And I understand what Glenn is saying is, if we can set the rules so that every time you add a generator, it doesn't destabilize the whole system, it will make the system planner's job a lot easier.
If you could do that, yes.
If you can do it.
Yeah.
And that's the final, and your conclusion is you haven't been able to find a way to do it.
That's right, yes. So that's
There are still jobs at National Grid.
I mean, do you believe that it's doable and you just need to spend longer and get clever and maybe use more sophisticated maths, or have you come up against sort of impenetrable barriers in trying to do it?
Oh no, I think it's doable, but yeah, it needs the maths has to be refined, and I'm going to have to get the right picture. So for me, the big advantage of talking to guys like you is to get the picture right.
But do you think it's okay? If you throw enough money at a problem, you always get a solution. But do you think it's doable just by doing math, or by spending loads of money?
Oh, just by doing maths, yeah. Yes, I don't do anything else.
Just a point of clarification. Your basic stability theorem about the systems that are interconnected assumes, I think, that there are two kinds, green blocks or red blocks, integrators or first order systems.
Oh, no, that was an example.
Ah.
So, I mean, the theorem is much more general than that.
Okay, so you can have higher order systems.
Absolutely, yeah. And that's the advantage of it being a frequency domain approach. You can have delays, you can have, yeah. Where's it gone? Past it. So that's the theorem.
You talk about relationships between tau and t.
That was an example.
Yeah, so you get...
Oh, so the point is there's the theorem which is entirely decentralized. Because you've got that decentralized theorem, which it only has to be satisfied locally, that allows you to come up with protocols which guarantee that it's satisfied locally. So the protocol then guarantees that this condition is satisfied everywhere.
Linearity is part of that theorem.
So linearity, yes, it absolutely is. It is purely small signal. Yeah.
Right.
Yeah.
Okay, but even then, even to establish that for the power systems, that's proving be difficult. I mean, going beyond linearity will be a different challenge.
Oh yeah. So it's precisely small signal stability.
So what I understand is basically what's happening now in practice is actually people are doing that, but I think without your mathematical framework, because of course there is a grid code and no generator will be connected unless it satisfies certain stability conditions.
Yes.
So this is done in a conservative manner, obviously.
Without guarantees.
Without guarantees, but basically based on the practice and without your underlying theory. So if I understand your presentation correctly, you are providing theory for the practice which has been around for 100 years. So
you can put it like that, yeah.
In order to improve the practice, right?
Well, you can use it to improve the practice, that's right. Okay.
But I'm not even providing the theory, I'm providing the theory which is done it elsewhere and it might. Might, yeah.
We'll take the opportunity to slight pause.
Okay.
So I'd like to thank Glenn for his very interesting talk and for contributing to such vibrant discussions. Let's do that.